Oxyacids, obviously, contain oxygen. Let's consider H2SO4, which is an acid, as we know, sulfuric acid, and calcium hydroxide, which is a base. Notice that these two have very similar structures. In each case, we have an OH bonded to a central atom, and we might ask, why is one of them an acid and the other a base? A good rule of thumb is in the upper right corner of the screen. Water attacks a molecule where the polarity is greatest. Just like a wolf attacks the part of the herd that is weakest, water attacks a molecule where the polarity is the greatest. Let's show you what we mean here. The difference in electronegativity between sulfur and oxygen compares how to that between oxygen and hydrogen. If you look on the periodic table, sulfur and oxygen are very close together, which means their electronegativities aren't that different. The electronegativity difference between sulfur and oxygen is smaller than that between oxygen and hydrogen. This means that in solution only the H is released. Water is going to attack between the O and the H because that's where the polarity is the greatest. On the other hand, the difference in electronegativity between calcium and oxygen is larger than that between oxygen and hydrogen. This means that in solution the entire OH group is released. This all goes back to water attacking a molecule where the polarity is the greatest. On this acid, the polarity is greatest right there at that OH bond. The polarity is greatest on the right here at the OCA bond. When comparing related oxyacids, remember this, and you will see it again on the next few slides as well. Anything that draws electron density away from the donatable H makes for a stronger acid. Anything that draws electron density away from the donatable H makes for a stronger acid. Let's delve into that a little more deeply. Related oxyacids comparison number 1. For oxyacids with the same number of oxygen atoms, acid strength increases with increasing electronegativity of the central atom. Let's decide among these three acids which of them we would predict would be the strongest and which the weakest. And let's refer in the lower left corner, anything that draws electron density away from the donatable H makes for a stronger acid. These are all the same, except one has a chlorine in it, one has a bromine, one has an iodine. Chlorine is the most electronegative of those three, and so it would draw electron density away from the donatable H more than the bromine atom or the iodine atom. How about in this case? Which of these would we predict would be the stronger acid? Everything is the same except the central atom. In one case selenium, in one case sulfur. If we look at in the upper right corner where those two are on the periodic table, sulfur is more electronegative. It's going to draw electron density away. We would predict that the one with sulfur would be stronger, the one with selenium would be weaker. Let's look at a second trend. Related oxyacids comparison number 2. For oxyacids with the same central atom, acid strength increases as the number of oxygens attached to the central atom increases. Well, if you increase the number of oxygen atoms, you certainly are more able to draw electron density away from the donatable H. If we compare these two, the one on the bottom, which is bromous acid, has 2 oxygen atoms compared to hypobromous acid on the top, which only has 1 oxygen atom. Of those two, which is going to better be able to draw electron density away from the H, and that is definitely going to be the bottom one, which means those H's are more likely to pop off. How about this case here? The more oxygen atoms you have, the more you can draw electron density away, the more polar you're going to make that HX bond, and water is going to attack right there, and that H is more likely to pop off. How about a third trend? This comparison deals with carboxylic acids, which contain the carboxyl group. There are any number of ways to represent this. I've shown a few of them here, and then we have a representation of these atoms in space with the carbon double bonded to one of the oxygens, single bonded to another oxygen, and then R, I don't know what it stands for, I say it's the rest of the molecule. Any number of things could be hanging off the carbon in that direction. These are the largest category of organic acids, and for carboxylic acids, acid strength increases from adding additional high electronegative atoms. So if we compare these three, we can see that they are identical, except the top one has 3 H's in this location. The middle one has 1 H and 2 fluorines, and the one in the bottom has 3 fluorines. Which of those is best going to be able to draw electrons towards it? And that would be the one on the bottom. So we would predict that it would be the strongest acid, and the one on the top would be the weakest. Anything that draws electron density away from the donatable H makes for a stronger acid, whether it's a more electronegative atom or additional of the same highly electronegative atom. Anything that draws electron density away from the donatable H makes for a stronger acid.